Greetings and welcome to another installment of QuantSlob. This is 9 in our basic application series. This time around, part 3 of our mini-series on continuous quantities. If you have not already, you may want to check out part 1 and part 2, especially if you're doing this as part of a lesson plan. Also, you may want to take advantage of our QuantSlob channel About page for information on ready-made playlists for your convenience, enjoyment, and edification. We're going to continue with our discussion of continuous quantities and continuous distributions, but we're going to do it by contrasting continuous distributions with something with which we're already somewhat familiar. So let's return to a familiar discrete distribution, the distribution of card rank in a population of 52 cards comprising a standard deck of playing cards. Recall that we created here in the middle column integer rank, an integer rank attribute. If you haven't seen our foundational series and you're seeing this for the first time, all we've done here is we've converted the card's rank label value to an integer value. The idea is to simply convert the rank label to a quantity. Here is the distribution shown as a plot or a line plot. And to be very clear, what we're doing here is we're simply describing the distribution of the integer value rank in our population of 52 cards. There's no probabilities here. As we learned back in our foundational series in our probability edition, a theoretical random sample of a single element, a card in this case, from a population implicates a random variable from the attribute. The probability distribution is identical to the attributes distribution in the population. Now, this is admittedly a conceptual formality, but it's really important and it will save us a lot of grief down the road. So here we go. What we're looking at here is a so-called probability mass function, PMF for short, or actually more accurately what we're looking at is a graphical representation of a probability mass function. If we don't like looking at the plot, after all, I can't just assume people enjoy my line plots as much as I do, we can express this as a table. Just like the one we looked at a moment ago, except here you can see that we have assigned on the far right column each value of the domain to a probability as opposed to a proportion. So let's, just as an exercise, make use of this probability mass function. Let's call our integer rank value random variable x. So what, for example, is the probability that x equals 10? The idea, of course, is that the PMF here maps a value of the discrete random variable directly to its probability, explicitly to its probability. And this may be getting a little ahead of ourselves, but just as another example, we can use our probability mass function to calculate the probability of a region of multiple values. So, for example, what's a probability that x will be greater than or equal to 10? This is a region of values, and we can easily get to our answer simply by summing up all the probabilities associated with the values, 5 over 13. Okay, getting closer to continuous distributions now. I'm thinking of a particular continuous variable, and I want to convey this visually like we did with our discrete variable. And as we know well now, with a variable with a discrete finite domain, we can often visually show the relationship of domain values to the respective probabilities with a table. However, a continuous variable has an infinite domain. This makes using a table to enumerate the domain essentially impossible, so tables out, at least as far as enumerating values explicitly. We also used a line plot, of course, which we just saw, or a line height plot for variables with discrete finite domain. But if we try this with a continuous variable, we run into a handful of issues. First, we can't really plot an infinite number of purple lines here. The other issue is that if we think of our x-axis here, the abscissa, as being ordered, that is, numbers to the right are greater than the ones to the left, if our domain is dense, and it is, no matter what x1 and x2 are, there are still an infinite number of domain values between them. So a line plot is out of the question. And so what do we do here? We're going to pick this up in part 4. You're going to want to make sure to check that out, part 4 of our continuous quantities mini-series. And that's it. That's going to do it this time around. Thank you so very much for tuning in. Dearly appreciated as always. And don't forget to stay tuned for more QuantSlob.